All right, so this is a pilot implementation project. We did a bridge approach slab project with UT El Paso. And part of that implementation is look for lightweight materials as an embankment fill material. So this particular one is going to be focusing on one such application. This is a 5-6022. And now this is a little bit over exaggeration, but nevertheless, you do have a bridge approach slab settlement, huge amount of problem in the state. We have several bridges here that have embankment heights anywhere from 15 to 30 plus feet. This particular one that what I'm going to present has 40 feet. So where do the settlements of this bridge approach slabs come from? We know it comes from subgrades, natural subgrade foundations underneath your fill material. A lot of times fill material itself will consolidate with time, because even though we supposedly use a select fill, sometimes we have fill that have high plasticity. So they tend to experience settlements, primary consolidation type. You do have erosion, side erosion, rainfall and all others can take away on an embankment, on the slide slopes. You will see sometimes washing of material, fill material. So if you add up other types, like including type of loading, traffic loading, all these things can cause significant settlement. So if you look here, the TxDOT, this is a study done by here Texas A&M, and 40% of Texas bridges do have the settlement, or we simply call bump issue. And again, that year 2003, I'm pretty sure this is much more now, is around $7 million. This is a study conducted by CO under Dr. Briad here. So how do we repair them? What are different ways you can repair them? Here I put only a couple of them. There are more other ways you can repair them. You can do on the foundation soils. And the ones I listed here is excavation and replacement. Remove all the foundation that is a bad, nasty clay, which consolidate a lot. So remove that and put a good quality fill. And again, that can be expensive, but that has been tried. Preloading surcharge load. And this is done really if you have a soft clay. I'm talking about more really like a Boston or San Francisco area where you do have embankments. They do have to preload them because the natural sub foundation soil is extremely soft, undergo primary, so you have to load it, whatever the load is going to come from your structure, preload it, and then let it consolidate fast, and then take out that material and then put your structure on top. And then other things are vertical drains. You have stone columns is one of them, like are also you call sand columns you can use, are also prefabricated vertical drains, which are your PVDs. And the other thing is deep mixing, which we use in our regular project. Deep mixing is really a stabilization of native soil, a native foundation soil that is weak in soft nature, and we stabilize with soil cement. In this particular one, we tried lime cement application. Now looking at the other side, you have the embankment backfill material. There's a lot of studies going on Federal Highway, mostly on geosynthetic reinforcement and like segmental reinforced walls. That's been very popular. It actually came from Colorado DOT, and that's another one you can do. And you can also use some MSC wall types. Again, you can also do grouting, which in this particular example I'm going to present, we do have tried a micro grouting, didn't help much. And the other popular one is the lightweight fill material. And that's the one I'm going to focus more on today as my presentation, on lightweight fill embankment material. Here are the 4 types of embankment fill materials you have here. You have expanded polystyrene, which is your EPS material. That's the one I'm going to be presenting today. And again, that's a lightweight type of material that has been used all over the world in cutting down the settlements. You do have shredded tiles. You can mix with soils, and it can be a good fill material. And then again, cellular foam material that has been used. In fact, last month in Europe, I've seen the cellular material that is in market that they use as a lightweight material. And then expanded clay shell, which we have studied on one of the project sites for State Highway 360, expanded clay shell. Again, if you look at these material properties here, again, if you look at the pounds per cubic feet, and that clearly shows you the lightweight nature of the material. Typical fill material, you're talking about 100 pounds per cubic feet. So starting with ECS is around 30 to 60, so half that weight. And then look at this one, Geofoam, almost 2 pounds per cubic feet, very lightweight material. This is the one I'll be talking about it. Again, the cost is an issue, and they're not cheap. They're actually, once you have particularly ECS and other types of material, they can be used, but they come much higher cost than the dirt that you use in the fill material. But again, you have to look at some application areas where maybe it makes more sense than other areas. So I will talk a little bit at the end of my presentation on where it could be applicable. So the one that we looked at is EPS Geofoam. You're talking about 40 to 85, it's around $50+, per cubic meter there. And again, they come in large blocks like this. So this is your foam material. Now, when I mentioned I'm using foam material on the highway, a lot of said, you must be crazy. How do you put a foam under a truck? It's going to crush. No, foam has a cellular material. It has a sufficient strength. It can absorb. And in fact, it's used on high-speed train embankments. They can very happily take heavy traffic, a heavy dynamic nature of loading of a big train. So it really works pretty well. So it's defined by ASTM. Good thing is they have ASTM standards on this material, so construction usage can follow the standards also. It's a block or polymer or planar rigid cellular foamed material used in many applications. In fact, I'll be happy to send you some nice reports done on Geofoam. There are so many applications, and primarily cutting down the settlement because you're putting a lightweight material. And even though the documented nature is more than 30 years, I know the first application is late 60s. They're using Geofoam in geotech area. So it's been there for years, but it's catching up much more now. Okay? So just to show you the material, 100 times lighter than soil. Again, 20 to 30 times larger than some lightweight other types of material. Easy to handle, 1 or 2 person can carry. Construction is very quick. I'll show you the slides that will cover you how much time we took to complete this process. Very limited labor activity. It's not it doesn't take that long. Okay, so this is the project where we are doing this implementation. This is the US 67 here. This is the State Highway 174. It's in Johnson County. Okay, it comes under Tech.Fort Worth District. Again, the district is very helpful in giving us this thing. It was not that easy to sell the idea of using Geofoam as an alternative because cost is very high. And we have help from both Austin and also the Fort Worth District, Richard, and the district engineers. They all helped us. And then the reason for that is, if you look at it, this particular bridge really has settlements of 17 inches since 1995. And these are the settlement that we documented during the construction of this foam material. Huge amount. Almost, if you look at 17 inches, 1995, almost came as 1 inch per year. Within every second year, they had to repair this section. They had to stop the thing. And this has a heavy truck traffic is going around this area. So every time they repair, it's almost taking 4 to 6 weeks of construction or repairs. That's delaying a lot of construction in the whole thing. And when we did finally convince that this is a good approach, and the way we did is we didn't ask them to remove the whole 40 feet of embankment, and this particular embankment is 40 feet. And we know that's going to be very expensive. So we said, let's try something unique, hybrid type. Leave some part of your embankment and put 1/3 of your, maybe around 7 feet or height of 6 to 7 feet of your foam material. In this particular case, we put 6 feet on top of this one. So that when you place this foam, you really had to place a nice granular layer at the bedding layer. And that's what you're seeing here, sand layer. And underneath the sand, you have a geo membrane that is used for covering because you want the foam to be protected from your infiltrating oil leaks coming from your trucks or something. That can soften the material. And again, these are some of the construction process slides here. You can see the compaction, the sand layer that was placed, and then you can see the foams placed. And these are your connection players, the barbed one. So between them, you don't want any sliding to take place, so you place them here. You can see here they are located here. And then they are placed here, and then you have this shape adjustment, cut down the corners wherever you want, how do you want it, shape it, you can do it. And then at the end, after you finish everything, you close it, and you place the whole thing on top, okay? So basically, that's your Geofoam material. Since as a part of implementation, we were able to instrument this thing. What you see here, 2 types of instrumentation. Blue casing, which is your inclinometers going from one end to other end. And the other one is pressure cells we have. And we put pressure cells both horizontal and vertical. And I show you some of our results here. So here is your instrumentation showing your 4 inclinometers, half the travel section on both ends. We have 2 here, 2 on this side here. So our students, we have our grad students collecting the data since 2012. We are going there into the site. Happy face, see? So UTS students are very happy. They collect the data. And this is a large data we collected over the last 4+ years now. And again, I will show you more of this information. We do have some settlements in this particular section, as you see with time. Some of the settlement came during construction, because when you place the construction, you still have to place upper base layer, and then you have to put your concrete pavement. So that was actually covered up. There is some construction settlement that induced, that was recovered, that was collected by our kilometers. And then over the time after it's open to service, we collected settlements also, which is showed here in this data here. The pressure cells showed, again, the two pressure cells that we picked up here at the foam level, showed the amount of PSI, which is, again, a small amount. And the foam itself will absorb a lot of the stresses coming from your load. So foam itself will capture it, so the amount of stresses it will transfer to underlying soils is much smaller. That means the stressing on the subsoils underneath the foam is going to be smaller, so settlements will be smaller. And that was the whole approach of why the foam is used. Foam itself will capture some of them. So for our test data, what we did is we initially have 2+ years of data. So how do we assume that data can we extrapolate them? So we used a very common model, which is hyperbolic here. And this is a hyperbolic settlement data. This is time and settlement using this alpha B approach. So showing you some of our collected data, we have elapsed time period since construction. These are some of the data collected, and we use this alpha beta. And then from this, when we calculated, again, this is 1.4 to 1.5. And this is based on initial years of monitoring data. So that's what we predicted. But again, we know these numbers are not going to be valid, because the more data I have, 4 years data, I have to adjust these numbers. This is something that has to be dynamically done. And again, we were able to get an extension of this monitoring phase, which started actually 4 months back. We started collecting more data now, and we anticipate much more of the settlement collections. Data will help us much more in the coming days. So I'll show you a little bit here. So we looked at the data, and then here is our small section of foam. Again, we didn't put the whole area, right? So this is like hybrid section. And we tried to put all the traffic loading and everything, and we used the EPS 22, so we input everything, and then we tried to calculate what it takes for different types of embankments. How do you design it? So for that, first thing we did is just a Flaxis analysis, which is our finite element. So we looked at all our lab data from your materials, including foam. We input everything. And if you look at some of the settlements, what we picked is around 1.6 inches at the surface. So this is the settlements what we have collected over the time period. Again, the settlement what we collected is using a static loading on the pavement. We did not use a dynamic nature loading. So within like a short time frame, we saw that settlement is around 1.6. Whereas the settlement what we observed is somewhere around here is when it reaches this 1.6. That is the difference between those two is basically in the modeling, we put the load right from the day one, completely not changing. Whereas in real field, it's a dynamic nature, so we didn't include the dynamic nature. Plus, initial stiffness is not accounted in our modeling, which we're probably going to do with the flag. And then we know the settlements are very well predicted, so what we went back and did is, how do we come up with a simple approach? And so that we can calculate, you tell me an embankment height, and I should be able to, you tell me the type of soil properties, and I should be able to tell you what is the thickness layer that will be most cost effective and most optimized. So for that, this is a simple equation actually. So it's a bearing capacity, it's a soil capacity, foundation strength is here, undrained soil strength is the factor of safety. This is the load coming from your pavement, traffic, and then this is what you put the fill on top. The fill is here, again, here is the fill. And if you look at here, this is your foam. Gamma is unit weight of your foam, plus whatever the area that is in contact. So we came up with a simple equation, and if you know the soil properties of the subsoil, I should be able to tell you for different types, based on how you want to design, I should be able to tell you what is the thickness of your foam material from this particular chart. And this will give you the thickness of the foam, and depends on the factor of safety, how much you want to be. If it is an embankment bridge within an urban area, you don't want a repair to happen, use slightly higher factor of safety. But if you can live with a slightly, like around 2 or 1.5, where the traffic is not going to be a major issue or control or repairs, probably you don't need to put too much of a foam. So it's again cost approach. It all depends on where the site is located, how much repair will mean, how much of impact is going to be to the traffic. So you could use that approach. So one thing that you may come and say, okay, where is your settlements here? You are only showing the strength here. There is a settlement approach. Here, this approach will tell me what is the minimum thickness, so that the foam can be placed based on the foundation strength. Then after this, we can calculate using the equations, and then automatically the settlement will be much less than what you have, because you're replacing your soil with a lighter weight material. So settlements automatically will satisfy if you design with this approach. So in one way, with the two different equations, we have addressed it with just simple one approach, because second equation is automatically satisfied because you're replacing a material with a lighter material. So that's why we do not have to include it. So okay, we did, the student did a nice work. So we want to check and see if it really works or not. So for this particular case, we took our site and also took some sites that are reported in the literature. I-15 pavement widening project is a big project. In fact, it is a project of the year by ASCE, and there they have used huge amounts of foam. In fact, that's one of the largest projects where geofoam is used. So we actually used that project, some of the specifications from that project when we developed specifications for US 67. So we were able to collect from the Utah DOT some of the information from there. So here, you can see here, based on what their calculations, our numbers, based on the numbers, our actually approach equation pretty nicely, balancedly works very well. So it's an approach that is actually, it's not just based on US 67, we can also validate our data from other locations. And I want to mention here, a lot of work, if you look at geofoam, comes from Norway. And the Scandinavian countries, they sit on top of a mucky soil, almost like a quick clay. And it's one of the worst clay. Actually, the minute you go and dig within like 6 inches, you will get the high water table. And then on top, you go and stir the soil with an auger, you will make that soil liquid. And I think if you do YouTube, quick clay of Norway, you have a video that shows. Sometimes if your neighbor does a drilling, your home will start having settlement issue. And this is a very common problem there. That's where the most improvised ground improvement solutions come that part of the world. Finland, Scotland, although Scotland also further north of Scotland have soft clay. So a lot of nice work on settlement issues come from there. So large embankments are supporting both transportation, traffic, plus also trains. They all come from that region. So there's a lot of conferences on geofoam actually takes place over there. So in this current year that monitoring we are doing, we're also looking at the integrity of the whole system, because we put the foams in the middle travel lane right under the bridge area. And the side we have still slopes, and we have again a significant rain that we had in May. So we're looking at the data using some LiDAR data to look and see, because we do see some side surface slope, because you're putting two different materials. There's again, we didn't slope the foams. We just stacked the foam right in the middle. If we can do like a tapering, probably would have been nice, but we know that would cost us more. We didn't have that liberty with that in this particular project. But we learned from this project. So we are looking at this data and see if there is anything, and we're also looking at the profiler. We do see a recent data. We have a small increase in our settlement. And again, in May, we have almost 20 inches rainfall in that particular location. And this small increase, the settlement is only on 1 kilometer we have noticed it. We want to monitor that one. Again, that total amount is very small. It's probably not going to make any difference to the roughness. We won't even see any repair, but still, we want to monitor and see if we can learn from it. And again, I just want to say, this is the slide I always want to say, because research is always fun, but this really happened. One of our grad students collecting data, he was trying to push our inclinometer in one of the casing. We do have a lid. I don't know who opened the lid, maybe Richard. But somebody opened the lid, and then there's a snake sitting inside. But now student is pushing. The student is from Thailand, and they know king cobra, right? He was pushing it, so he was feeling soft thing, and then when he pulled it out, this snake was wrapped the thing, and I heard he jumped 20 feet, from the embankment. So this is not, again, research can be dangerous, but research can be very productive and can give good solution. We monitor this project, we will learn it. Again, this is the first of its kind. Have we done some things different? Yes, but again, we were very fortunate we got this project thanks to Fort Worth leadership. And I really think I want to acknowledge TechStart, both Richard, Jimmy, and Wade, all the folks. And then RTI office, Joe Adam is our project coordinator, and Wade, Ariel, and Sonia were very helpful. Again, our students are wonderful. They are very willing to take risks, like this project. So again, I think with this, I'm happy to answer any questions you may have.